Today I'll be discussing the benefits of applying petrophysical models to shale reservoirs. Open hole log data will be used as input to my analysis. As output, I'll generate 4 petrophysical models. Fred will then demonstrate 3D visualization of these models. He will also pick a target service and plan a horizontal well. We'll provide some conclusions, followed by answering questions if time permits. At the end will be a wrap-up and discussion of a few next steps. Benefits of applying petrophysical models. Basic open hole log data can be used in PRIZM to generate the following 4 petrophysical models: a lithology model, saturation model, organic carbon model, and a rock mechanics model. These models provide geoscientists and engineers added detail and insight to shale reservoir characterization, used in field studies and regional play projects, evaluation of infill and step-out drilling programs, completion designs and recomplete or refrac evaluations, and data room preparation or analysis for sales or acquisitions. In today's hypothetical case, we are given open hole log data from 3 vertical wells drilled within a township. I'll analyze and evaluate a prospective shale section and build a composite log displaying the 4 petrophysical models of lithology, saturation, organic carbon, and rock mechanics. The input data will be from triple combo and sonic logs, in other words, quad combo logs, consisting of caliper, gamma ray, SP, resistivity, density porosity, neutron porosity, bulk density, PE, and compressional wave sonic. One well also has a dipole sonic and sidewall core analysis, which includes shear wave sonic data, X-ray diffraction mineralogy, and total organic carbon weight % measurements. This is the study area. It's a township containing 36 square mile sections. There are 3 vertical wells numbered 1, 2, and 3, drilled in that order. The first well, well 1, was drilled as a science well where additional dipole sonic and sidewall core data were taken. Here's one input quad combo open hole log from which I'll build the output petrophysical models. The prospective section is approximately 1,500 feet thick. The upper half appears to be a good baseline shale. The lower half exhibits an increase in gamma ray count associated with increased activity developed in the other log curves. Here's the increase in gamma ray count and the activity on the resistivity, porosity, density PE, and sonic curves. The hot gamma ray may indicate presence of uraninite, which may be associated with an increase in kerogen content. This is typical of many shale reservoirs. If I scroll through the 3 wells, you see the same log profiles in all wells. This is well 1. Here's well 2. And here's well 3. Then back to well 1. The first petrophysical model will be a lithology model calculated on a volume % basis. Equations can be found in PRIZM's user-defined equations, in other words, UDE, the UDE dialog box. I'll mention shale volume specifically here because V shale will be calculated using bulk density and neutron porosity, not gamma ray. This is because the presence of uraninite associated with kerogen makes the hot gamma ray inappropriate for accurate V shale calculations. The 4-mineral PRIZM external model, or in other words, the 4-mineral PEM, will be used and calibrated to sidewall core XRD data. This is the PRIZM user-defined equations dialog box. Notice it contains a couple predefined PEMs, the 3-mineral PEM, the 4-mineral PEM, and an Archie interpretation. I've copied the 4-mineral PEM and renamed it to Shale Analysis 4-Min. This log displays results from the 4-mineral PEM next to the XRD mineralogy data used for calibration. Both are calculated on a volume % basis. The 4-mineral PEM calculates the 3 principal mineral endpoints, calcite, quartz, and dolomite. The remaining volume is assigned to V shale as the 4th mineral. The trick here is to calibrate the 4-mineral PEM so that the mineralogy or the lithology model matches XRD data measured from the sidewall core analysis. I've already calibrated the 4-mineral PEM, and here are the results. The match is not perfect, but you would not expect it to be perfect. However, the match is close. Notice the lithology model is calibrated. Once the lithology model is calibrated, it can be applied to the other wells having no sidewall core data. I've added the lithology model to the quad combo log, and here is the composite log. Notice there are several carbonate buildups in the lower half of the section, which could be potential reservoir rock. These buildups correspond to the hot gamma ray interval. If I scroll through the 3 wells, you see similar carbonate buildups in all wells. This is well number 1. Here's well number 2. Here's well number 3, and then back to well number 1. And this is the interval of carbonate buildup I'm referring to with the hot gamma ray. The next petrophysical model will be the saturation model. Equations can be found in PRIZM's user-defined equations dialog box. I'll use Archie as a reasonable first estimate for water saturation in bulk volume water. The first question that comes to mind when using Archie is, what is the RW? I'll show you an unconventional use of the picket plot to estimate RW at formation temperature for shale reservoirs. However, there's no free lunch. You must know or assume either a maximum water saturation or a minimum water saturation, in other words, an irreducible water saturation, or preferably both. Here's a picket plot, which is a graphical representation of the Archie equation. The picket plot is simply a cross plot of porosity versus resistivity in log-log space. Since I've already calculated V shale using bulk density and neutron porosity, I've got V shale color-coded on the cross plot as well. Over on the right side is an index log showing where the cross-plotted data occurs on the log. Now, before I jump into interpreting the picket plot, I'd like to clean the data up a little bit by first applying a V shale filter. Now, I've already built a V shale filter, and right now all the data is being presented. So let's say I filter V shale by, let's say, 30%. In other words, only display data that has a V shale of less than 30%. That cleans the data up quite a bit. And you see that the data now is concentrated on the carbonate buildup zone of interest. So that cleaned the data up pretty well. But still, looking at the data, I need to clean this data up a little more, or at least investigate further the data that's cross-plotted. In particular, I see an outlier of data here to the southwest of the data field, outlying away from the main data field, cross-plotted further to the northeast in the cross-plot. I'm curious to see where that data occurs on the log. So I'm going to lasso those outlying data points. And you see on the index log that these outlying data points are kind of scattered up and down the log and not really concentrated in the zone of interest. Those data I'd like to filter out of my analysis. Now, where does the rest of the data occur? If I lasso the main part of the data field, you see that those data occur in the carbonate buildup zone of interest. So before I jump into my picket plot analysis, I'm going to clean the data up a little bit, a little more, by including only the data that's in the main data field, that data. So now I'm ready to start my picket plot analysis. I open up the picket plot window. Here's the window. And as I mentioned before, the picket plot is simply a graphical representation of the Archie equation. So the picket plot parameters I've got set up, the Archie parameter of A I've got set to 1, and the Archie coefficients of M and N I've got set for 2 and 2, which is a good starting point for the analysis. You see in the picket plot window here, the second cell displays the calculated RW from the picket plot. Below those cells are the SW lines, the lines of equal water saturation, and I've got those set at 60, 40, 20, and 10%. If I go to the picket plot here, you see there's a blue line. That blue line defaults automatically to 100% water saturation. So behind that line to the northeast lie the 60% water saturation line, the 40%, the 20%, and then finally the 10% line. So you see how these lines are distributed across the picket plot. You notice that they're linear in log-log space, first off. And also, you see that water saturation increases from northeast to southwest. Conversely, water saturation decreases from the southwest of the picket plot to the northeast. So the conventional use of the picket plot in analyzing a conventional reservoir that has a water leg, the conventional use of the picket plot then is to lay the 100% water saturation line so that it bounds the data that represents the 100% water saturation in the log. And in a conventional reservoir, if there's a water leg, that 100% water saturated data is represented by the data that's plotted furthest to the southwest in the picket plot. So in a conventional use of the picket plot, the 100% water saturation line may be placed, maybe something like, give or take, something like that, to try to bound these data down here furthest to the southwest. Well, that's a conventional reservoir. We're dealing with unconventional reservoirs, namely shale reservoirs. And we know that in this section, we don't have 100% water saturation. However, let's assume that we at least know the maximum water saturation, and we may have gotten that from core analysis or your experience in working the field. So let's assume we know, at least know or assume a maximum water saturation possible in this interval of interest. And let's assume that it's 40%. So if we're assuming that the maximum water saturation is 40%, then instead of laying the 100% water saturation line on the data furthest to the southwest, we maneuver the 40% line, maybe something like that, so that it bounds the data furthest to the southwest. And then the RW is read off the picket plot, conventionally off the picket plot, by extrapolating the 100% water saturation line to 100% porosity and reading the corresponding resistivity as the RW, which is reported here in this cell. Now, after I fitted my 40% water saturation line to the maximum water saturated data, I'm not too comfortable with how these lines fit the data. It looks as if the slopes are off. I like to adjust the slopes of these lines so that I get a better fit of the data. If I go back to my Archie coefficients, we know that the M exponent is the cementation exponent, but the M exponent also determines the slope of these lines in log-log space. So if I change the M value from 2, and let's say I make it 1.5, you see the slopes of the water saturation lines change. And if I reposition the 40% water saturation line, maybe something like that, give or take, I get a better fit of the 40% water saturation line to the maximum water saturated data plotted furthest to the southwest in the data field. And then the RW then is just simply read conventionally off the picket plot by extrapolating the 100% water saturation line to 100% porosity and reading the corresponding resistivity as the RW, which is reported here in this cell. Now, as another example, let's assume I don't know what the maximum water saturation is in my interval of interest. Well, let's assume I have a pretty good idea of what the irreducible water saturation is. Let's say we got that from core analysis or from other studies done in the area. So in this example, let's assume that the irreducible water saturation is 20%. The 20% line is this line right here. So we know that the maximum water saturated data plots furthest to the southwest in the data field. Then conversely, we know that the minimum water saturation then is plotted furthest to the northeast in the data field. Those data represent the irreducible water saturation. So if we're assuming that the irreducible water saturation is 20%, we simply maneuver the lines of water saturation so that the 20% line bounds the data furthest to the northeast, maybe something like that. So here the 20% water saturation line is bounding the minimum water saturation data cross-plotted furthest to the northeast in the cross-plot. Once that's done, then the RW can be determined by extrapolating the 100% water saturation line to 100% porosity and the corresponding resistivity being reported as the RW. Now let's assume we have the best of both worlds. We have a pretty good assumption of what the maximum water saturation is and what the irreducible water saturation is. I've already fitted the irreducible or the minimum water saturation line to the data furthest to the northeast in the data field. And I'm looking now at the 40% line, and I think I can make it a better fit. It doesn't quite bound the data as well as I think it should. And to adjust that, we can go to Archie's N coefficient, which is the saturation exponent, but it also determines the spacing of these lines of equal water saturation. So let's say I change the N coefficient from 2 to 1.5. You see that changes the spacing of the water saturation lines. And if I reposition the 40 and 20% lines, maybe something like that, I get a better fit of the data. I get a better fit of the maximum water saturation line, and I get a better fit at the same time of the minimum or the irreducible water saturation line. Once that's done, again, I read the RW conventionally off the picket plot by extrapolating the 100% water saturation line to 100% porosity and reading the corresponding resistivity as the RW. So there you have it. There's an unconventional use of the picket plot to estimate RW at formation temperature for an unconventional reservoir such as a shale reservoir like we're looking at today. Now that an RW is determined, a saturation model can be calculated and added to the composite log. Notice the carbonate buildups exhibit various water and hydrocarbon saturations. Two zones in particular look prospective. These two buildups down here, here's the saturation model, those two zones. If I scroll through the three wells, you see how the saturations vary in the carbonate buildups from well to well. Here's well number 1. Here's well number 2. Here's well number 3. Then back to well number 1. The next petrophysical model will be the organic carbon model calculated on a weight percent basis. I'll be using Passey's delta log R equations found in his December 1990 AAPG bulletin paper. Passey's level of organic metamorphism, in other words the LOM parameter, will be calibrated to sidewall core TOC data. By doing this, the delta log R curve separation can be transformed to total organic carbon on a weight percent basis. The resulting TOC can then be used to identify potential kerogen-bearing hydrocarbon source rock. I've already built a user-defined equation set containing Passey's equations and named it Shale Analysis Delta Log R. This log displays the delta log R curve overlay next to results from the organic carbon model. Also posted are the sidewall core TOC data used for calibration. Both the model and core TOC values are calculated on a weight percent basis. The trick here is to calibrate Passey's LOM parameter so that the organic carbon model matches TOC data measured from the sidewall core analysis. I've already calibrated the organic carbon model, and here are the results. The match is not perfect, but you would not expect it to be perfect. However, the match is close. Once the organic carbon model is calibrated, it can be applied to the other wells having no sidewall core data. I've added the organic carbon model to the composite log. Notice the carbonate buildup interval has good TOC, indicating hydrocarbon source rock potential. If I scroll through the three wells, you see how the calibrated TOC varies from well to well. This is well number 1. Here's well number 2. Here's well number 3. And back to well number 1. The last petrophysical model will be the rock mechanics model. Equations can be found in PRIZM's user-defined equations dialog box. Young's modulus, Poisson's ratio, and brittleness index will be calculated from compressional and shear wave sonic data. The Rickman and Mullen SPE September 2008 paper describes the calculations in detail. These petrophysical rock properties can be used to indicate relative brittle and ductile intervals. They can help target horizontal drilling or vertical completion zones. They identify possible frac barriers, and they can provide completion engineers with physical properties needed for hydraulic frac modeling. I'll also demonstrate use of a cross plot to determine cutoffs for generating a brittleness index flag curve. This flag curve can be used for facilitating interpretations, generating maps, and building cross sections. Here's a cross plot of Young's modulus versus Poisson's ratio with color-coded brittleness index. You see how Young's modulus is scaled 0 to 10, increasing downward on the y-axis. Poisson's ratio is scaled 0 to 0.4, increasing from left to right on the x-axis. The calculated brittleness index is color-coded. You see, and also Young's modulus and Poisson's ratio are cross-plotted in linear space. So a cross-plot of Young's modulus and Poisson's ratio scaled in this way, you see by the color code of the brittleness index that brittleness increases from the northeast to the southwest in the cross-plot. Now let's say I'm interested in building a brittleness index flag curve displaying those intervals that have a brittleness index of greater than 0.5. Well, I'll need the cutoff parameters. And you can tell by the color scale here that a brittleness index of greater than 0.5 would be roughly these data here. So if I put my cursor right about there on that corner of the box, you see what the cutoff parameters need to be for Poisson's ratio and Young's modulus. It looks as if we need a Poisson's ratio of 0.26 or less and a Young's modulus of greater than 2, along with a brittleness index of greater than 0.5. Now you can build a brittleness index flag curve using those cutoff parameters, which I've already done. I've built a brittleness index flag curve using cutoffs from the Young's modulus and Poisson's ratio crossplot and posted it with the rock mechanics model on the composite log. This is the finished composite log showing the input quad combo open hole log data along with the output petrophysical models of lithology, saturation, organic carbon, and rock mechanics. The Young's modulus, Poisson's ratio, and brittleness index curves are scaled so that brittleness increases from left to right. See how the brittleness index flags make for an easier interpretation of the rock mechanics curves. Notice the carbonate buildups exhibit brittleness laminae interbedded with ductile laminae, which should enhance hydraulic fracturing. Two zones of carbonate buildups emerge as prospective horizontal drilling or vertical completion targets. Again, these two zones down here. And the resulting organic carbon and rock mechanics curves. If I zoom into the perspective interval and scroll through the wells, you see how the brittle-ductile relationship varies from well to well, along with the other three petrophysical models. Here's well number 1. Here's well number 2. And here's well number 3. And back to well number 1. Fred will now demonstrate 3D visualization of these models. Take it away, Fred.
Thank you, Mark. Now that Mark has completed his analysis, I'm going to walk you through a workflow of how to use this interpretation to create a target surface, visualize it in 3D, and design a mechanically drillable well plan. First, I will view the map and smart section of the wells used in the analysis. From there, I will select one of the wells and launch it in PRIZM. In PRIZM, I will examine the petrophysical attributes and extract the attributes of interest within the zone of interest for mapping. The smart section cross-section will be used to pick the target surface based upon the petrophysical attributes. The target surface will then be incorporated into the smart section frame builder for 3D geomodeling. In the map view, a 3D probe region will be selected and launched to automatically load all of the contained 3D objects into the Pro 3D scene. The smart section cross-section will be displayed in the 3D scene as a fence diagram with the interpolated calcite attributes between the wells. The high concentration of calcite attribute display will be enhanced using the color histogram control. Finally, the calc target surface will be turned on to delineate the calcite attribute away from the fence diagram. In the map view of Smart Section, a projected line of section will be laid out for the planned well to create a vertical section cross-section. In the vertical section, Well Planner will be used to capture the digitized target points along the calc target surface to make an on-the-fly well plan. This well plan can be exported to Excel for delivery to the drilling department for their final well planning. Lastly, we'll examine the planned well in Pro 3D. This is a map view in Smart Section displaying a line of section of the 3 wells Mark used in his analysis. Next, I'm going to select one of the wells in the shale well school wells and display it in PRIZM. I'm showing the completed petrophysical model within the PRIZM template. Notice there are a number of calcite-rich benches of interest on the log. I'm going to focus on the bench between the Calc 2 and Calc 3 markers. This bench is particularly calcite-rich, has good TOC and water saturation, and shows brittleless laminae intercalated with ductile laminae, which should enhance the frackability of the unit. I will next use PRIZM's curve data statistics to extract the calcite and the Brit flag attributes within the zone of interest. I will then save each zone of interest as an isomap later to help delineate any attribute trends in the map view. This is the map view of the calcite and brittleless attributes. The calcite attribute is color-coded with the darker blue color indicating the high calcite concentrations and the red color low concentrations. The brittleless attribute is displayed as contours overlaying the calcite attribute. Notice both attributes have a strong southwest-northeast orientation. This orientation will be important in determining the azimuth of our planned well. Next, I'm going to launch the cross-section and Smart Section containing the 3 wells Mark used in his analysis. Then, using the surface picking tool in Smart Section, I'm going to pick the calc target surface within the Calc 2 and 3 benches. The picks are automatically added to the database and modeled in Frame Builder using triangulation and minimum curvature smoothing. By placing the calc target in the correct stratigraphic order within the surface constraints hierarchy in the Geosurface Model Properties dialog box, the calc target surface will conform to the higher priority surfaces and be modeled over the extents of the B1 surface. This is a map of the calc target structural surface. Notice the red box displayed on the map. This is the 3D probe region previously drawn. By selecting this region, right-clicking and selecting Display in 3D, all of the 3D objects within the extents of the probe will be automatically loaded into Pro 3D. Pro 3D is GeoGraphix Enhanced 3D Visualization Interpretation module built using Microsoft Xbox gaming technology. It has automatically loaded all the wells, surfaces, base map, log templates, and log curves into the scene. These objects are listed in the tree view at the left side of the window. I'm going to turn off the visibility of the surface and display a fence diagram of the calcite attribute interpolated between the wells of the cross-section. Notice the higher resolution PRIZM template displaying the complete analysis for each well in the fence diagram. By using the histogram control, I can selectively filter the color histogram to highlight the colors of interest. In this case, the blue color is indicative of the calcite attribute. Next, I'm going to add the calc target surface to the scene. Notice that the surface follows the blue calc attribute in the fence diagram. By adding the calcite and brittleness attribute as overlays on the surface, I can more clearly discern the structure and attribute trends that I'll be using to plan my well. Returning to the map view in Smart Section, I'm going to lay out a line of section using the well at the southwest corner of the area. My planned horizontal well azimuth will take into account the trends of the calcite and brittleness attributes. My pre-formatted vertical section projected cross-section displays the modeled surfaces and the planned well projection position. Notice the calc surface is the dashed red line between the calc 1 and the calc 2 surfaces on the cross-section. Next, I'm going to launch Well Planner. Well Planner is an LMKR plugin to the GeoGraphix, and I will listen as I pick the target surface points on the vertical section and create the well plan on the fly. Notice that the surface, kickoff, heel, targets, and toe points are listed for every point picked on the vertical section. The Calculate tab displays the Well Planner vertical section and plan views of the well plan. As long as the borehole is in green, it is mechanically drillable according to the kickoff point, heel points, target points, and toe point, and the approach and lateral dogleg severity parameters. The Display tab displays a diagram of the well geometry for QC purposes. The Export tab displays the survey position log and build rates for the planned well. This report can be exported to Excel for delivery to the drilling department for the basis of their final design. All the while the target points were being digitized in the cross-section, Pro3D was updating the well bore view display in real time. If the plan is modified in the vertical section view or in Well Planner, the 3D view automatically updates with the latest data. The 3D scene can be particularly useful for preliminary anti-collision detection.
Thanks, Fred. PRIZM petrophysical models provide geoscientists and engineers added detail and insight to physical properties needed for shale reservoir characterization. The petrolith shale petrophysics workflow is conducive to fast turnaround analysis, for example, if you're working in data rooms, as well as more detailed projects like field and play studies. PRIZM is an efficient and cost-effective alternative to other petrophysical software and has the added benefit of full integration with GeoGraphix and LMKR applications.
PRIZM is a powerful multi-well petrophysical modeling application that integrates seamlessly with the other GeoGraphix applications to support comprehensive reservoir characterization. Attributes extracted from the PRIZM model can be used to guide the creation of a 3D surface created within Smart Section with Frame Builder to extend the interpretation over the reservoir area. These 3D attributes and surfaces are easily visualized along with other 3D objects in Pro3D for better insight into the trends, scale, and character of the reservoir. Well Planner captures target points digitized along the key surfaces to easily create a mechanically drillable well plan for delivery to the drilling department. We hope you enjoyed the webinar and found it informative and useful for getting the most out of your GeoGraphix software investment.